So I guess a little background then. Probably about 2007 when Open Solaris released, or 2008 when Open Solaris released their 2008 .06 edition, I think. They introduced ZFS as the default install. And so at the time I played with it and I wasn't impressed. I thought the performance was absolutely horrid. I thought the level of administration that was needed to run it was just as bad. And so I had a very bad taste of it in my mouth. And then about 3 years ago, I saw that there was a project from the Lawrence Liverpool National Laboratory. They had a contract from the Department of Defense to port Solaris' ZFS to Linux. And so with this bad taste in my mouth, I thought this isn't going to go anywhere, but I'll take a look at it. And my taste has changed. And now XMission is moving ZFS into production. I've given talks at Ohio Linux Fest, as well as the Southern California Linux Expo on ZFS, and now I'm here. So hopefully you guys enjoy it. So the whole presentation is online at my website, aarontoponce.org, /presents, and then you can see all of my presentations there. And that's my email address. And feel free to use this under the CC by SA license. So here's my motivation for why. First off, how much time do I have?
Till 8:30 or 9.
8:39. Okay. Okay. See, I brought a whole slew of USB thumb drives. I'm going to use these hopefully for demos, so you guys can see it in action. So my motivation is really this link. Oh, I don't have internet, but that's okay. Let me get back to where I was. And I just lost it. My motivation for ZFS is that link, which is actually a Google Trends page, and it shows the differences between cloud server and cloud storage. And what's interesting is to see these two graphs on how both of them are increasing, and likely due to Amazon and other moving to the cloud type technologies. But all of a sudden around 2007, you see cloud storage just skyrocket at an exponential pace that cloud server just doesn't. Storage is becoming a hard problem to solve. And I don't know if anyone has it completely right. We see NoSQL databases. We see clustered file systems. We see big data like Hadoop and other things. I think ZFS fits in this picture somehow. And so anyway, I'll discuss that. And then I thought this was kind of fun. I saw this on this website. But if 1 grain of rice equaled 1 byte, then here's some interesting statistics about how much grains of rice a megabyte would be, and a gigabyte, and a terabyte, and so forth. So a zettabyte would be a Pacific Ocean size of rice. So anyway, I thought that was entertaining. So what is ZFS? ZFS is a 128-bit file system. At least that's what the internet tells us. It's actually technically not true. It's more like a 78-bit file system. But we could easily recompile it for 128-bit support. Some of the limits, you can have a ZFS file system that is 2 to the 72 bits in size, which is large. In your ZFS pool, you can have 2 to the 78 number of ZFS file systems that are each 2 to the 72 bits in size. In fact, Jeff Bonwick, the lead developer behind ZFS, mentioned that just because we can doesn't mean we should reach those sizes. And he even does some mathematics on the back of an envelope type thing, where he says that to get to that size of storage, you'd need enough energy that could boil the oceans. So it's likely that we won't be getting to that size, but the support's there. ZFS is a copy-on-write file system. This is a data storage technique where rather than modifying the data in place, you make a copy of the data and then store that copy elsewhere. So intentionally, data is fragmented. But fragmented data isn't always a bad thing. If you do it intelligently enough, although you might incur some performance penalty, you don't have to incur a lot. What's nice with Copyonwrite file systems is we get some really interesting things for free that I'll discuss in this presentation that make the trade-off worth it. It's a combined file system, volume manager, and RAID manager, so I don't need to have a separate software or hardware RAID. I don't need to have a separate volume manager like LVM. It's all built in together. Has native support for SSDs for write and read acceleration, native support for deduplication and compression, also native support for encryption. However, this is not free software. An interesting history behind ZFS is Jeff Bonwick had the idea in 2001 while working at Sun Microsystems to come up with a modern file system. And they released it in 2005. They released it under the open source CDDL license, also known as the Cuddle license. However, when Oracle purchased Sun Microsystems in 2009, they took the source code of Solaris proprietary, and they have not released any source code after the acquisition of Sun. So we have the source code from the time Sun released it and all their revisions up until the acquisition of Oracle, and we don't have the source code afterwards. After that acquisition, Oracle introduced encryption natively into ZFS. We don't have access to that code. And as a result, we have not pushed out our own encryption because we don't want to break compatibility with Solaris and other file systems or other ZFS operating systems, supported operating systems. I think we're getting to the point now where we realize that's a pipe dream. And so we've introduced what's called feature flags, where we can add and remove our own little features into ZFS at will. One of those is showing good, solid traction for encryption. So we'll probably have our own encryption soon. But as for the time being, only Oracle Solaris has native encryption support for ZFS. ZFS checksums the data from top to bottom. The developers of ZFS identified all the places that we could have data corruption in our file system and wanted to close those gaps. So part of that was checksumming our data, includes metadata as well as the data blocks. And further, ZFS is developed from the ground up. There is no legacy UFS or other Unix file system code in ZFS. In fact, ZFS operates more like an ACID-compliant database than it does a traditional POSIX file system. And I think we'll see how that works as we go along. So first, let's talk a little bit more about the Copyonwrite. Again, it's an advanced storage technique where we take the block that we wish to modify, and rather than modifying it in place, we make a copy of it and store the new data elsewhere, and then update the pointers to point to that data. So data gets fragmented. But as an extension of Copyonwrite, we have some interesting things that ZFS does. One bullet point that I missed that I was thinking about on the way down. First off, ZFS groups all of its writes into what are called transactions. Transactions are numbered, and each transaction is written in order. They're never written out of order. These transactions are grouped into pools called a transaction group, or a TXG, and that gets flushed to your platter, your spinning rust, if you want to talk about it, every 5 seconds by default. Okay? What's interesting about these flushed writes is they're atomic. If you know your A in ACID for databases, it stands for atomic writes, right? It's the same thing. You either get all of the data or you get none of it. There's no intermediary data. So there's no possibility for file system corruption. Now I want to make something clear and distinguish the difference between file system corruption and file corruption. ZFS guarantees, practically, say with 5 nines, that you're not going to corrupt the file system. You can have file corruption, however. That's not difficult. Say you want to write a 10 gigabyte file and you start writing and then cut the power halfway through. You're going to have partial of the 10 gigabyte file. You'll have a corrupted file. Or if you're using non-ECC RAM and maybe you have a bad bit stuck in address that's always giving a 0, when ZFS gets the data from RAM, it trusts that data. So even though there's a bad stuck bit, ZFS doesn't know any different. It'll checksum it and store it into the platter. So you can have file corruption. But file system corruption, ZFS is guaranteed to protect us against. And so that's what we're looking at. ZFS uses a Merkel tree, or a hash tree. It has a root node and then all these children nodes underneath it. Each block write basically gets a revision number. This Merkel tree will keep up to 128 revisions before cycling the number. This gives us snapshots for free. And I'll talk about snapshots in a second. But I can take a copy of this Merkel tree at any given moment in time, and that Merkel tree describes every block on my file system. So when I have a copy of that Merkel tree, I know exactly what my file system looks like at that specific point in time. ZFS doesn't have a need for a file system check. Traditional journaled file systems have file system checks because a write operation is actually 4 sequential writes to the disk. You write to the journal. First you open it and write to the journal. Then you flush your inodes to tell the journal where you're going to be putting the data. Then you actually finally flush your application data. And then finally you close up the journal. If there's a power outage between writing the inodes and writing the blocks, then you have file system corruption. And next time you boot, you'll be forced into a file system check to fix the inconsistent inodes with the inconsistent data. And it may or may not be recoverable based on the journal. Because we have these atomic writes, we're writing the inodes, we're writing the logs, we're writing our data, we're doing all of this atomically. Again, it's all or nothing. So we don't have a need for a file system check. However, we do have what's called scrubbing. ZFS scrubs data. What this is it looks at the block and it checksums the block and then checks that result with the stored checksum. If they don't match, and we're using redundancy, we'll look elsewhere in the array to find good data or to recalculate the good data, fix it, and then store it onto disk. Scrubs don't happen automatically. There's something you've got to manually do. So you could put them in a cron job and say schedule it once a week or something.
So it's an online operation?
It is an online operation, or you can take it offline. But yeah.
Is it faster offline?
No, not really, no. But one interesting thing is it is smart about the scrub. It knows how much data is occupied on disk. And obviously, because of the Merkel tree, it knows where the data resides. So we don't need to scrub the entire pool. We only need to scrub the stored data. So it's a little intelligent about what we need to check. So ZFS, and this is what I think is interesting, is we do have full native kernel level support for ZFS with Linux. There is a Fuse-based project to get ZFS into Fuse. It hasn't seen a lot of work, and people haven't really put a lot of effort behind it because it is a Fuse-based project. Fuse being, the user space file system. This is native kernel modules. You load them up into the kernel. You have ZFS loaded in the kernel as a legitimate file system. And you can go to zfsonlinux.org. And this is where that the Lawrence Livermore National Library project is being executed. Okay? It's on that website. There's an Ubuntu. Go ahead.
It just can't ship with you can't ship it with the kernel.
Correct. So
because of the cuddle.
Right. Because of the cuddle license, it's incompatible with the GPL, which the mainline kernel source code is developed under. And so we can't ship the cuddle source code with the GPL source code. But that doesn't prevent you from compiling it yourself.
Will it give me the notice about tainting your kernel?
No. Because just like, say, running the Opera web browser, which is proprietary on your laptop, same sort of thing.
NVIDIA.
Or in NVIDIA, yep, if you install NVIDIA or the non-free Flash plugin. Yep. As an administrator, you can install free or non-free software all day long. That's your prerogative, not the kernel's prerogative. We just can't ship the ZFS source code with the kernel source code. But if you want to compile it separately and load it up, that's up to you. And so that's what this project is about. I created this short link so it fit on a slide. But if you wget that link, it's just in this case, a deb file for Ubuntu and Debian-based operating systems. dpackage-i, install the deb, and it'll set up your apt sources. And then you can do an apt-get update, and then an apt-get install Debian ZFS, and you'll have kernel level ZFS, kernel space ZFS installed. So that's what I've done on my laptop. And so we're going to go ahead and play with that. But let me first introduce the commands that we're going to be dealing with. With ZFS, there's only 3 commands. Zpool, which configures all of your ZFS pool stuff. This is your RAID array. This is your volume management. If you needed to do maybe like compression or anything that would affect the entire pool, it's done through this command. ZFS is what we use to set up our file systems. This would be analogous to like a makefs. Okay? And then ZDB is used for debugging and consistency information. You will rarely ever need to actually use ZDB. 99% of the time, you'll be doing Zpool and ZFS stuff. But if for any reason you suspect that your ZFS file system is corrupt or it's not consistent, something's not behaving quite right, ZDB is available for you to dig into the bowels of ZFS, so to speak, and get some of that information. OK, so let's build a beginner pool. So let's see. I think I'll just use these small ones. So I didn't do enough. So I've got these little 16 gig USB thumb drives. I'll just plug these in. And then we'll set up a pool. And some of them have been reused and repurposed for various stuff. I'll just do those 4 for now. So let me go to my terminal here. We'll make everyone see that all right. So I think I should have E, D, C, and B. And we're not. Why are you going up? I don't know. Let's do this. My E and A key are failing me, so. OK, so SDB, C, D, and E. All right. So the way we create a new pool is just with Zpool Create, and then we give it a name. In this case, I've named it Tank. And I'm going to stick with Tank as my pool name throughout the presentation. So I create a pool, Zpool Create Tank SDA-BC. Go ahead and do that. Create Tank SD. Now in my case, I don't want to use SDA. That's my main hard drive. DSDE. And of course, using USB, it's going to be a little slow. Shouldn't take this long, though. There we go. And then I can run Zpool Status to see the status of my ZFS pool. So in this case, I can see the state is online. I named it Tank, as it can see. Tank is online, and then drives SDB, C, D, and E are also all online. Those numbers on the right, the read, write, and checksum, if there's ever any read or write errors or checksum errors, these are counters that will show up how often those have occurred. Okay? Because there's a new pool, I haven't encountered any errors yet. So now this brings up the idea of VDEV. So we need to get a good handle on this if we want to understand our ZFS pool. First off, VDEVs are always striped in ZFS, striped across VDEVs. Okay? We have 7 types of VDEVs. We have disk, which we just saw in this previous slide. I'm using 3 disks. Each disk is operating as its own VDEV. So because in my case, I have 4 16 gig drives, so the size of my pool would be 64 gigs. All right? Other VDEVs are file VDEV. You can use files. The mirror VDEV, a standard RAID 1 mirror. ZFS introduced RAID Z, which is a distributed parity-based RAID. So we have RAID Z1, RAID Z2, and RAID Z3. The RAID Z levels are a VDEV. And then we have these special VDEVs, spare, log, and cache. So let's look at each of these. The DiskVdev, again, dynamic striping. I have 4 16 gig drives, 4 times 16 is 64 gigs. The size of my pool is 64 gigs. No redundancy, but I get some awesome throughput on reads and writes. When I'm creating my pool, I can use the full path /dev/SDA, or I can use any block device that's already listed in /dev. Like you saw earlier, I just gave SDA space SDB rather than /dev/SDA, so forth. It's best practice, however, to use the devices found in dev disk by ID. The reason why, these are unique identifiers for your drives. Unfortunately, motherboards don't present their SATA ports in a logical manner to the kernel. So on one boot, the drive plugged into SATA port 1 might be SDA, but on the second boot, it might be SDB. Now, if I were just using, say, disks, just the DiskVdev, or mir or RAID-Z, this wouldn't be a problem because all the metadata is stored on the disk. If it's SDB one time and SDD another, it's no big deal. ZFS is intelligent enough to rebuild the array. However, if I get into these special devices like spare or cache or log, if my log device is SDD on one boot and then it comes up as SDA on the other, it wants to be a member of the core pool and I can have file system corruption. But if you use these identifiers that Linux exports, and these are just model names and serial numbers of your drives, this follows the drive no matter what drive letter it gets assigned. If it's SDA one boot and SDD the next, no big deal. It's always still going to be that name. So best practice to use these. As you can see, they're lengthy. They don't fit on slides very well. So I'm going to stick with SDA, B, and C. But in practice, you should be using the dev disk by ID stuff. Okay? The file VDEV, this is kind of interesting. You can create a ZFS pool using pre-allocated files on an already existing file system. The files have to be pre-allocated. They can't be sparse. And you must provide the full path when you're building the pool. A word of caution. The consistency of the file system, or of your ZFS file system, is only going to be as good as the file system that these files reside on. So if you're building this on ext4, then the data quality or reliability will only be as good as what ext4 can provide, right? So this is not something you want to do for production, but this is great for testing scripts, for maybe just trying to get familiar with how ZFS works and how the user space command works. Maybe you want to dig into the bowels and really play around with ZDB, which, by the way, you can totally physically, manually muck up your file system. Files would be a great way to do that. Build a ZFS, put some fake data in there, and have at it. But nevertheless, it's available. The mir VDEV is a standard RAID 1, just like you're already aware of. It needs at least 2 or more disks. And in this case, when I do my Zpool Create, I say Zpool Create tank, and then I put that mir keyword in front of it. So anything following that mir keyword until I reach another VDEV belongs to it. So in this case, this is a 4-way mir. If these were all 16 gig drives, my Zpool size would be 16 gigs, right? 4-way mir. So nothing really too terribly interesting there. What is interesting, though, are these RAID-Z VDEVs. This is something introduced by ZFS. And these are distributed parity-based RAID arrays. RAID-Z1 is a single distributed parity. RAID-Z2 is a dual distributed parity. And RAID-Z3 is a triple distributed parity. Now, RAID-Z1, it's similar to RAID-5, and I put that in the slide. And RAID-Z2 is similar to RAID-6. But it's not exactly RAID-5. RAID-5 must calculate a stripe width that is the width of all of the disks in the array. RAID-Z is more of a dynamic stripe width. If, say, my chunk size is 64K, and I write out 128K worth of data, then I only need to write out 2 chunks. I don't need to worry about finishing off the rest of the chunks to fill the size of the stripe width, like a standard RAID 5 or RAID 6 would. Because all of the metadata is stored in the file system, and that includes the RAID information and the volume information and the file system information, it knows where the data resides. It doesn't need to fill that stripe width. This is kind of a good and bad thing. It's good in that, depending on your data, you probably are not always filling out that stripe width. And so there's less data to check. There's less parity calculations to work on. But it gets a little hairy when you have a disk failure. How does ZFS know how to recreate the data in the event of a disk failure? So we can have a penalty performance or penalty hit in that regard. However, here's some examples. RAID Z1 does require a minimum of 3 disks, 2 disks for the stripe to store the actual data and 1 disk for the parity. RAID Z2 requires a minimum of 4 disks, again a 2-disk stripe and a 2-disk parity. And RAID Z3 requires a minimum of 5 disks. So again, if these are all 16 gigs in size, every Zpool would be 32 gigs total. Doran.
Is it possible to, if you have 4 drives like you do in your example, to do one 32 gig redundant? So you have like a RAID 1 across 2 of those. So you have
okay.
RAID 10 kind of thing?
So you want to do like a, I think I understand, maybe you want to mirror SDA and
so
SDB.
Instead of having a 4-way mirror, you have a 2-way mirror across.
Like a RAID 10?
Yeah.
Yeah, you can easily do a RAID 10. You could just create, you would say something like Zpool create tank mirror SDA SDB mirror SDC SDD. And then it gets striped across those mirrors, but the devices inside the mirror are mirrored. So yep, you absolutely can do that.
How would that performance compare to the RAID Z1?
So that's a good, and I kind of hinted this in the slide. RAID 1 will always outperform parity-based RAID. I'm just going to settle that myth right now. If you don't believe me, build standard RAID 5 against the RAID 1 mirror and benchmark it and see how your benchmarks come out. You'll find that you'll get almost a 50% performance increase on just a standard RAID 1 mirror. RAID Z2 and RAID 6 is slower than RAID Z1 and RAID Z5, and RAID Z3 is even worse because of all the parity calculations that you're off to. But RAID mirrors are expensive. You lose half of your disk, right? Not every IT budget has that sort of checkbook. So this is available where you can get more bang out of your space while maybe taking minimal impacts on performance.
So with the RAID Z1, if you have 5 disks, then you would only be losing 20% of your, because you'd still only have 1 stripe.
Right, so if you had 5 total disks, yeah, so you would lose 20% to the parity, and the other 4 would be used for storage.
Now RAID, if I remember right, RAID Z, can it do different size disks?
It can. So just like in standard RAID, if all of my disks were different sizes, it will take the smallest drive and use that to calculate the pool for across all 3. So you will have wasted disk on the larger disks. With that said, let's say that my RAID Z1, they're all 1 terabyte disks, and now I want to upgrade to 2 terabyte disks. ZFS has the ability to auto-expand the pool. So I can replace the first drive with a 2 terabyte disk, let the data repopulate, then replace the second drive, let it repopulate, then replace the third, and after I replace that third, ZFS will automatically expand the pool to include the 2 terabytes. Yeah, it's awesome. Something you don't get with hardware RAID controllers or even Linux software RAID. So, yep. And for those watching, I apologize. My nose itches really bad right now. So I'm rubbing. I'm not picking. So let's look at the additional VDEVs. A spare VDEV is to add a hot spare in the event of a disk failure. A log VDEV is the ability to take what's called the ZFS intent log, or the ZIL, and move that onto a separate logging device like a fast SSD. And I'll talk about more of that in a sec. And then the cache is a read-intensive cache device, something, again, you could use on an SSD. And I mentioned that cache and log devices should be on fast SSDs, or if you can afford it, DDR drives or NVRAM drives. And so here's some examples where I do a Zpool add to tank, and then I say I want to add a spare, and here's the spare SDA. Or I want to add two log devices, SDA and SDB, and I want them mirrored. Or I want to add some cache devices. Here's SDB and SDC. Okay? Let's look at these a little more intently. The separate logging device, also referred to as the slog, will store what's referred to a file called the ZFS intent log. In fact, in the ZFS community, you'll often hear the term slogzilla. It's reference of taking the ZFS intent log that normally would reside on your platter disks and moving that to a separate logging device. Okay? So the slog device and the ZIL are one and the same if the slog does, in fact, exist. The slog device is write intensive. Just like a journaled file system, ZFS will write the data to the log device first. And when the log device has the data, then we'll flush that data to platter. If in the event we have a power outage while we're flushing to platter, that's okay. When we bring our pool back online, that transaction will still exist in the slog. And we can read from the slog and then flush those remaining transactions that didn't get flushed. We can go ahead and flush those to disk. As a result, because it's write intensive, you should consider the life expectancy. SSDs typically have, it depends on the process, but you can expect maybe 1,000 writes out of an SSD before you start to see failure. So if you have maybe a 120 gigabyte SSD at 1,000 writes, that means you could effectively write 120 terabytes worth of data if it has wear leveling algorithms before you can start to see the chips on the SSD fail. So you'll want to keep that in mind. The separate logging device should be small. You don't need to make it big. The reason why is the logging device is designed to decrease latencies on synchronous writes. So you have an application that wants to do a synchronous write to the file system. The separate logging device steps in the way and says, I've got the data, and it only took me a millisecond to act that back instead of maybe 40 or 50 milliseconds that your pool would normally take. So the application can continue doing the rest of its processing quicker and faster. But the throughput is going to be limited based on your slowest device in the file system, and these are going to be your spinning platters, right? So if you think, let's say I can flush 200 megabytes per second sustained of sequential writes to my platters, which is fast, I admit. Let's just pretend. By default, ZFS flushes the transaction groups every 5 seconds. So that means at 200 megs a second every 5 seconds, I could sustain a bandwidth of about a gigabyte of data per 5 seconds to platter. Which means if I wanted a separate logging device, a gig should be sufficient. Doing a 2 gigabyte or larger separate logging device really isn't going to buy me anything because my platters can only sustain a gigabyte of writes every 5 seconds.
You can't put an SSD with wear leveling, it would buy you.
Yeah, so if the pool does get backed up,
right.
if your transaction groups do get backed up, the separate logging device can store that.
On the drive. If the drive was bigger than what you really needed.
Oh, right, fair. Right. So
your drive would fail not as quickly.
So what most people will do is actually use one SSD for both the slog and the cache, and they'll partition it.
Right.
And they'll give a 1 gig partition for the slog, the rest of the cache, and that partition effectively moves across the SSD due to the wire leveling, right? So, yep. And you should mirror it just in case, if you have multiple log devices, just in case one dies. You can still replay those transactions in the event of a catastrophic failure.
What happens if that dies? Like if you don't have it mirrored and that dies?
Then any transaction groups that are in there are lost. So, yeah. So the log, the separate log is just as critical as the data in your pool. And you should treat it as such. So, however, the cache is a little bit different. So ZFS has what's called an ARC. It stands for the Adjustable Replacement Cache. And it's an implementation of IBM's Adaptive Read Cache. So IBM looked at modern file systems, and keep an eye on the time, looked at modern file systems and saw that we have a problem with caching. We typically use what's called a most recently used, least recently used caching mechanism, much like a conveyor belt. I read data off of the platter, and I store them into what we refer to as a cached page, right? This is now the most recently used page. Through time, this page will get older and older and older until we reach the end of my cache. Then it's discarded from cache, and if I want it, I need to read it off of platter again. If during that time on the conveyor belt it gets reread, it just gets pushed back to the start of the conveyor belt, and it begins its life again. This is how Linux caching works with XT4 or other file systems. This is how many, many file systems work. ZFS takes most recently used and least recently used pages in the cache, but it also takes most frequently used and least frequently used pages. So it keeps track of two things: how often it's getting accessed, as well as how long it's been since it was accessed. Okay? So maybe, let's just say my conveyor belt, for example, has a duration of 5 minutes. But I'm accessing something maybe every 10. Maybe like a Google bot is crawling my site every 10 minutes. Well, that means I'd continue to take it out of platter, put it on the conveyor belt. 5 minutes later, take it out, put it on the conveyor belt. It's inefficient. ZFS recognizes that here we have something that's frequently accessed. The counter on accessing this is high. So we'll keep this in cache, even though it might not be the most recently requested page. So we can keep track of both things disjointly, which is kind of nice. The ARC is stored in RAM, and you can have what you call a level 2 ARC. So the ARC in RAM would be referred to as a level 1 ARC. This level 2 ARC, you can extend that cache to something like an SSD or an NVRAM drive. And the idea is that, well, my installed system memory is only so big. Maybe I only have 16 gigs or 32 gigs on my server. But my websites and my databases I would like to have cached, and they occupy 200 gigs of total disk space. It'd be nice to fit all of that in cache. The level 2 ARC is there for you to do that. Okay? So anything that spills out of the level 1 ARC that would normally go to platter now spills to that level 2 cache, and it stays there until that level 2 cache fills. Then it finally spills off to platter, if that makes sense. The adjustable replacement cache should be read intensive. It should not be write intensive. If you are doing more writes to the cache than you're doing reads, you need to relook at your specific setup and see how you can make adjustments to make it read intensive. Your adjustable replacement cache should be as large as possible. Like I said, most people will use maybe 1 or 2 SSDs and partition it, and they'll give a gig to their write-intensive slog and then give the rest of the space to the cache. The more the cache, the better off we are, right? And it can be volatile. If we have a power outage and the cache is gone, no big deal. We'll just repopulate the cache at the next boot up, right? So we'll have a little performance penalty while we're populating the cache, but once the cache is fully populated, we're back in business. Okay, so let's look at a hybrid storage pool then, something that implements everything. So I'm going to come back here to my pool, and I'm actually going to destroy this pool and recreate it. So I need more drives. So I'll add more. So I now have 7 16 gig USB drives. So B, C, D, E, F, G. I think one of these actually might be dead, which is OK. So let's go ahead and create a hybrid storage pool. So we'll create a RAID 10, and we'll put on, so that will use up 4 devices. We'll use one of them as a hot spare, and then we'll just use a full device as a slog and a full device as a cache. Don't worry about partitioning it. It's just going to take too much time. Okay? So we'll do Zpool Create, give it a name, call it tank, and we'll mirror SDB, SDC, and we'll mirror SDD, SDE. Then we'll spare SDF, we'll log SDG, and we'll cache SDH.
There is no SDH.
B, C, D, E, F. Oh, we only had 6, didn't we?
Yeah.
All right, then we will forget the log, and we'll just do a big cache of SDG. Uh-oh. SDF. Let's do -F to force it. Failed, SDF, triparted. Maybe SDF is dead. All right, so maybe we won't get to do as much of a hybrid one as I wanted. CG, Do I have any mounted? I do, that's why. All right, let's go back to my example then. Should succeed. And then we'll do a Zpool status and take a look. So now we can see my VDEVs. I have a mirror 0 VDEV, a mirror 1 VDEV, a cache VDEV, and a spare VDEV. SDB and SDC are mirror 0, SDD, SDE are mirror 1, SDG in the cache, SDF in the spare. Pool's online, everything looks healthy and good. Cool. A couple more things about pools. Keep an eye on the time. We might go close to 9, if that's all right.
Another question.
Yeah.
So it can do mirroring and striping. Like the Linux RAID 10 driver can do some different layouts as well.
Mm-hmm.
Is there any way to do that with ZFS?
No. So
Bar layout.
So here's a couple things you'll want to keep in mind with your pool. First off, you want to keep all of your drives the same size. All of your drives the same spec. Don't mix 500 gig drives and 720 gig drives.
Except with the cache.
Right? Yeah. With the special VDEVs, you're all right. But with the DiskVdev, the RAID Z VDEV, and the mirror VDEV, keep the specs the same, the sizes the same, and also don't mix VDEVs. Don't create a RAID Z1 VDEV and a mirror VDEV and then stripe across the RAID Z and the mirror. Right? So I wouldn't want to have maybe a mirror-0 and then a RAID Z1-0. The reason why is it severely imbalances your pool. And it starts playing, ZFS starts playing favorites on where it stores the data rather than treating all the drives equally. So what ends up happening is you start using one drive more than another drive, and then you'll start to see drive failures on a consistent basis, or you'll start to see severe penalty problems or performance penalties. So keep all your VDEVs the same, keep all your drive sizes the same, keep all the drive specs the same. Okay? And then you'll be running in a best practice situation. So, but with that said, though, I could perfectly have a RAID Z. If I had 6 disks, I could have 2 RAID Z1s of 3 disks apiece. Right? I could have a RAID Z-0 with 3 disks and a RAID Z1 with 3 disks. Okay? And then it would stripe across those 2 RAID Zs, effectively creating a RAID 50, if you will. Right? So that's perfectly doable. Again, it always stripes across VDEVs. So add your VDEVs, and you'll get the dynamic striping automatically. With the RAID 10 in the Linux kernel, it's actually a non-standard RAID 10 because it should require 4 drives, but you can actually do a RAID 10 in Linux software RAID with 3 drives.
Right.
Kind of horky.
Well, it does the offsetting.
Right. Yeah. So you can't do a 3-drive RAID 10 with ZFS that I'm aware of. So.
But it'd be cool.
Sure. All right. So importing and exporting pools. Exporting pools offlines is how you would offline and unmount your ZFS file system, basically. What's nice about this is you could migrate these disks after you've exported them to another system, and then do an import, and your data will come all back online. If I had more time, I'd export these drives. We could put them in a bag and mix them up, and then plug them back in at some random order and import them, and it'll all come up cleanly. Okay? All of that metadata information is stored on the drive. What's also interesting is when you do an export with ZFS on Linux, remember that best practice I told you with using the disk IDs? If you do an export, it will use those IDs in the export. So when you do the import, you'll see the IDs automatically are set up for you. Okay, so ZFS is even, at least the ZFS on Linux implementation, is smart enough to prevent you from having that headache of corrupted data. When you do an export, it creates an etc ZFS zpool.cache. This could be useful for moving that file to the other system in case it has trouble importing the drives. You can read that cache file as like a helper to bring the drives online. Scrubbing and resilvering pools, as I mentioned, every block is checksummed. And by default, it uses SHA-256. This includes the metadata blocks and the standard file blocks. The reason it's checksummed is for something called silent data corruption. Silent data corruption is corruption that is not inherent to the operating system. It's inherent to outside factors like gamma radiation, or a bad SATA cable, or fluctuating power, or non-ECC RAM where you have a stuck address bit and it's always writing a 1 when the application wants a 0. Okay?
Or a bad disk.
Or bad disk, yeah. It's something external to the OS itself. So by checksumming the data, if my block or a byte gets corrupted, the checksum will fail, right? If I'm using redundancy, then ZFS has the ability to look elsewhere in the pool for good data. Let's take a mirror, for example, because it's simplistic. Let's say I have a 2-drive mirror, and an application needs to read data off of the drive. So ZFS comes to drive A and says, I need the data. Drive A delivers the data. At that point, ZFS will checksum the data and make sure the checksum matches before handing it off to the application. The checksum fails. We've got bad data somewhere in that block. So ZFS will move to drive B and ask for the same information. Give me the data here. Checksums it, the checksum is clean. So we give this data to the application, then ZFS will self-heal the data on drive A. It will go back to drive A, now that we have good data here, and replicate that data to make sure that the checksum passes. Okay? And this happens automatically. This is for free for you. However, you can also force that every block passes its checksum with a scrub, like I mentioned earlier. And that's just using the zpool scrub command. Resilvering is when you have a drive failure, and you put in a replacement drive, and ZFS needs to start repopulating the data on the replacement drive. With hardware RAID controllers or Linux software RAID, they're not aware of what data is file system data and what data is just random junk on the drive. So when you resilver, or I guess rescan, rebuild a drive using hardware RAID, it has to start from the very beginning of the array and work all the way to the very end. Even if you've only occupied 100 gigs of your 5 terabyte array, guess what? You're scanning all 5 terabytes. ZFS is smarter than that. It knows where your data is and where it's not. So if you only have 10 gigs occupied in your 5 terabyte pool, it's only going to resilver 5 gigs of data to fill up that drive, and then it's done. So ZFS resilvering is much faster, much more intelligent at rebuilding the data on the new disk than a standard RAID would.
Resilver across the network?
No, so ZFS is not a networked file system, and it's also not a clustered file system. So the resilvering will happen locally. Yep. I guess I should say if you built your Zpool using drives that were exported via iSCSI, or maybe a fiber channel target, then technically you'd be doing that over the network. But yeah, so it's got to be presented as a local disk to the system, I guess. A couple additional slides on Zpool, and then we'll get on ZFS stuff. Zpools have properties. This allows you to tune your ZFS pool to your needs. For example, auto expand. Remember how I talked about maybe your array is filled with 1 terabyte drives and you want to upgrade to 2 terabyte drives. Auto expand is off by default, meaning if you refill everything with 2 terabyte drives, it won't expand your pool. So set auto expand to on before you replace your first drive, then start your drive replacement. By the time you've done the last, ZFS will auto expand the pool.
Can you expand manually?
That's a good question. I'm not sure. You could look in the documentation afterwards and take a look. Auto replace, also off by default. This is what's used to pull your hot spare in the event of a drive failure. Some people don't like this. I can see why the developers implemented it, though. Just because you had a drive failure doesn't necessarily mean you want a new drive jumping in and fixing it. You know, maybe you're in the path of migrating your drives, or maybe you're going to upgrade. Or maybe you're just taking the data off and you don't care that there's a drive failure. So I can see the reasoning for not doing that. Or further, resilvering does stress the pool a little bit. And if this were to happen during prime time, you don't want customers getting pissed off because data's slow. You know, we'll fix the drive at 2 a.m. when we're off hours, right? So I can see why it's off by default. A shift equals 9 and A shift equals 12. Drives typically read and write in 512 byte blocks. Now we have this new advanced format drive, these drives that read in 4K bytes, or 4K, blocks, 4K byte blocks. When you build your pool, if you know that all of your drives are advanced format drives, then you can set the property A shift equals 12. 2 to the 12th power is 4096. 2 to the 9th power is 512. So by default, A shift will be set to 9 unless you manually say otherwise. This is something that can only be done at pool creation time. If you discover later, after you've created your pool, that your drives are advanced format, and you would like to take advantage of that, you'll have to migrate your data off, destroy the pool, and recreate it with A shift equals 12. Okay? And then Zpool health will show the status of your pool, useful for scripts, and things like Nagios. Some best practices and caveats. You should use 64-bit architectures for ZFS. Technically, it will work on 32-bit, but ZFS is specifically designed to take advantage of a lot of 64-bit technology. So use 64-bit systems with ZFS. You should use ECC RAM, and the more you can supply ZFS, the better. ZFS likes RAM, mostly for caching, for the ARC, so the more the better, but it should be ECC RAM. I have a wonderful, I think it's wonderful, post on my blog about why you should be using ECC RAM with ZFS. Okay? And I can share that with you at the end. Use whole disks instead of partitions. This gives ZFS the ability to take full advantage of all of the encoding mechanisms and the drive algorithms and stuff if you're giving it the full disk versus just a partition. Works fine with partitions, works better with full disks. Keep pools separate. It's not a big problem to have 2 or 3 Z pools on a single machine. But should you do it? Probably not. Probably a better idea to have a single pool per machine. Just to keep things administratively simple, to keep things cleaner, just all around less headache. In terms of performance, a RAID 10 will always outperform a RAID Z1, which will always outperform a RAID Z2, etc. When using RAID Z, there's this recommendation out on the internet that you should use a power of 2 disks plus a parity disk. So for example, with RAID Z1, you would have 2 disks plus parity, so 3 disks. Or 4 disks plus parity, so 5 disks. Or 8 disks plus parity, so 9 disks. Right? See that 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. And the same with RAID Z2 and RAID Z3. The reason why is this maximizes on space efficiency, and it also, the stripe size gets optimized with the parity, so you're not waiting too long to get the parity written to disk, or you're not waiting too long to get the data written to disk. So it gives us a middle ground, if you will, on space efficiency as well as performance. Use fast disk for your slog and L2 ARC. We covered that. You should be doing regular scrubs. Put in a cron job for SATA disks to scrub your pool weekly, like on a Sunday night at 2 a.m. Okay? Of course, the larger the pool, the longer it will take. And Zpool scrubs are ionized, so they won't get in the way of database writes and other stuff. So it may take longer on busy servers, but at least it'll stay out of the way. If you're using SAS drives or fiber channel drives, you could probably get away with monthly scrubs, but get in the habit of doing regular, consistent scrubs. And enable compression. There's really no reason why not to enable compression. Compression is cheap. It doesn't really tax the CPU. The space savings are immense, and you actually get performance benefits. Because maybe you have, say, a large MySQL database. If you put transparent compression on your Zpool, it could be, say, 1/8 the size. That means that when you need to read data, you're only traversing 1/8 of the physical drive platter that you would be normally. And it's the same with writes. You're only writing 1/8 of the physical drive platter that you would be normally. So reads are faster and writes are faster on compressed data. So I would strongly encourage just enable compression. Even if you don't get any gains out of it, maybe all you've got is like JPEGs, you might get something, and it's really not going to hurt you.
I was just going to say, if you know that your data is, like I've got a mid-TV server, it's probably not very compressible.
Right.
Is it?
Again, it's not going to hurt you. You're not going to see any performance penalties as a result. It's really not going to tax, it's really not going to tax your CPU, and you might get some space gains out of it. Probably not a lot, probably less than 1%, because it's already compressed. But it's not hurting you, so I don't see the reason why not to, right?
I've got something similar on the compression ratios on like 1.02 top. That's close to 50%.
Yeah. Okay, now let's move. I got about 20 minutes left, so I'm hurrying. Let's move away from the pool and onto what ZFS calls data sets. This is probably what you would think of as more traditional file system, but ZFS refers to them as a data set. First off, ZFS data sets have access to the entire pool storage. Okay? So if you have a 4 terabyte pool and you create a ZFS data set, it has access to all 4 terabytes. If you created 100 data sets, every data set, number 1 through number 100, has access to all 4 terabytes of the pool. This is kind of different. You're probably kind of cocking your head thinking, how does that work? The data sets are self-aware. Okay? Let's say I have 4 data sets on my 4 terabyte pool. Data set 1 is occupying a full terabyte. The other 3 know now that there's only 3 terabytes of available space left that they can occupy. Okay? And if data sets 2 starts chewing through 500 gigs, the last 2 know, well, we've only got 2.5. So they're self-aware of where the storage has been allocated and what they've got available. So to create a data set, we use the ZFS Create command. I have to provide the pool that I'm creating the data set under. So in this case, tank. And I just give it / and then I give it a data set name. So I could say ZFS Create, my E key, tank, and we'll call this, say, plug. Now I can do a ZFS list to see my data sets. Technically speaking, when you create a ZFS pool, the pool is a data set in and of itself. And it's already mounted to /tank, in my case. You could just start throwing data in there. Most people don't. Most sysadmins will create a data set with a name representative of maybe what they're storing or some sort of purpose for the data set. But you can see that my pool is 28.5 gigs in size, and tank plug has access to all the storage. If I create another one, let's call this slug for the Salt Lake Linux users group. And again, due to ZFS list, they both have access to the full pool. And we can start storing data and running. So let's get back to compression then. ZFS supports some different compression algorithms. LZJB, which was invented by Jeff Bonwick, it uses the LZ algorithms that you're probably familiar with in LZMA, XZ. If you have 7-zip installed, it uses the LZ algorithms. The nice thing with the LZ stuff is you get some really tight compression ratios, and it's really clean, and it's pretty stinking performant. Not as performant as gzip, but it's not as bad as bzip either, right? LZJB was designed to be fast. It's a fast LZ algorithm. You also have gzip levels 1 through 9 are supported, or the old canonical ZLE, which doesn't get you tight compressions, but is a speed demon. ZFS on Linux 0.6.1 introduced LZ4. This is faster than LZJB, and it produces tighter compression ratios. So I would encourage you to use LZ4 rather than the others, but you might have reasons, for using gzip or whatnot. But to set compression, you just say ZFS set compression equals, in this case, LZJB, and then I give it the data set name. Okay, in this case, tank/store1. Deduplication. I heard a sigh back there. Deduplication is the ability to deduplicate blocks on the file system. There's 3 types of deduplication. There's byte level deduplication, block level deduplication, and file level deduplication. All have their own advantages and disadvantages. ZFS went the block deduplication route. If you're familiar with Btrfs, which is the new hotness for the Linux kernel, they went file level deduplication. With block level deduplication, we have to keep what's called a deduplication table. This is basically a lookup table to say where my deduplicated blocks are on the file system. The deduplication table is capped at a maximum of 25% of your arc, okay? Which means that if that deduplication table grows bigger, it's going to spill to disk. If it spills to disk, you can kiss your performance out the window. Absolutely goodbye, it's gone, okay? You've got to keep your deduplication table stored in the arc. So, how do you know how much to store? A good rule of thumb is 5 gigabytes of deduplication table for every 1 terabyte of disk. This comes from the fact that each deduplicated block, roughly is stored about 320 bytes in the arc. Okay? Each block typically sits around 64K. If you have larger files, it'll migrate up towards the 128K range. And if you have smaller files, it'll migrate closer to the 4K range. But roughly, a good rule of thumb, 5 gigabytes of RAM for every terabyte. So if you had a 4 terabyte array, this means your deduplication table could theoretically be 20 gigabytes in size. Because it's 25% of your arc, that means that you, what did I say, 420? That means you need an 80 gigabyte RAM install to prevent your table from getting spilled to disk. And that's assuming that you're giving all of your RAM to the arc, which you probably don't want to do. Most people, most sysadmins will give a quarter of their RAM to arc. So at 80 gigs, you now have a 320 gigabyte RAM install just to keep your deduplication table stored in RAM. It's costly. It's very, very costly. But if your specific situation has highly duplicated data and you know you can take great strides with it, then it might pay off for you. But nevertheless, it can be costly. And here's what's interesting. You set it per data set, but it's applied pool-wide. So if I begin storing data in my tank plug data set that I built, and I put deduplication table on there, it'll start looking in the full pool for duplicated blocks, not just blocks that are residing in that data set. Okay? This means that if you decide it's been too costly and you want to disable it, ZFS doesn't retroactively duplicate the blocks. It will still keep and hold on to that deduplication table. Over time, that table will shrink because you turned off deduplication, but it won't disappear. So keep that in mind. Snapshots and clones. Snapshots are a first-class read-only file system. They are a legitimate file system. That Merkel tree that we talked about at the beginning basically keeps revisions of your blocks. As a result, we get snapshots for free. And all a snapshot is a copy of that Merkel tree. Okay? Now, ZFS internally will only keep up to 128 Merkel trees before it starts recycling through the old. But that doesn't mean that I can't take a snapshot of a Merkel tree and hold on to that data. And even if we've gone well past that revision in 128 beyond, I still have what that data looked like at that specific point in time. Much like walking out to a busy freeway, taking a picture with your digital camera, even though the freeway's changed, you have a digital picture of what that freeway looked like then. And that picture's not going to change. It's right there. ZFS snapshots are the same. Also, ZFS snapshots are cheap. They're instant. Because you're only grabbing the Merkel tree, you're not actually walking the file system to see what the data looks like. ZFS snapshots are instant no matter the size of your pool. To create a ZFS snapshot, you use the ZFS snapshot command. You provide the data set, and then to identify it as a snapshot, you put the @ sign at the end, and then give it a unique identifier. So in this case, I identified it as 001. So I could store some data. Let's go into tank plug. We'll write some data in there. Dev random OF equals random.img equals, we'll say, gig. I don't know if I want to do that much. We'll do 500 megs. Count equals 1. Why didn't that work? Let's see, how about we do, I know what I can do. We'll copy over my presentation. Downloads, zfs.tar.gz to here. Okay. So I'm going to go ahead and snapshot my data set. Tank, we call this plug, right? And then I give it a unique identifier. We'll go ahead with a 001, that's fine. Now to see my snapshots, I do a ZFS list with -t and then give it snapshot argument. And I can see I have a snapshot here. And it's a legitimate file system. So what's cool about this is I can walk right into this file system and start perusing the data, okay? If I do an ls-a, you'll notice this is all of my data, but there's actually a hidden .zfs directory that even ls-a won't show you. Kind of funny. And we can change this, by the way, but it's there. Now I have this snapshot directory, and in here, here's my 001. I go into 001 and list out my data. There's my random.img and my zfs.tar.gz. Okay? And even if
it also mounted?
It's not mounted. Nope. Nope.
That's the only way to get to that snapshot?
Right.
Can you mount it?
You can clone it, which you can promote it to a read-write, and then you can mount it. Yep. You can do that. What's interesting now is let's say random.img starts changing. When I took my snapshot, I had a representation of what that file looked like at that point in time. I need to keep that consistent. So if that starts to change, I need to make sure I bring in the data unchanged. Does that make sense? If additional data is copied into, maybe 3 and 4 additional files are created, they weren't part of the snapshot. So I'm not going to bring them into the snapshotted file system. But if, say, random.img got deleted, it was part of the snapshot. I need to make sure I have a copy of it, so the full file will actually be brought into the snapshot to make sure that I keep that copy on board. Okay?
Is there a way to have, do you have to manage, like if your disk ran out of space, is there a way to have it automatically start, just delete the oldest snapshot? Or?
So there is a POSIX shell script called ZFS Auto Snapshot. It's on GitHub. And its idea is you want to do regular and consistent snapshots, but you're only interested in keeping the most recent X number. And so what I've done with it is I've put it in cron to go every 15 minutes, every hour, every day, every week, and every month. On the 15 minutes, I only keep the most recent 4 of those snapshots and delete the rest. Of the hourly ones, I only keep the most recent 24 and delete the rest. Of the dailies, the most recent 30. Of the weeks, the most recent 8. And of the months, the most recent 3. So as the snapshot gets older and older and older, I'm less interested in the granularity of the deltas between the snapshots, right? But by default, it doesn't clean them up. You need to clean them up yourself. And that shell script that I mentioned will do that for you if you want to deploy that. What's fun about snapshots is you can send them to other Zpools, to other ZFS file systems. And if you think about it, you're sending a full file system in a consistent state to another location. Compare this to rsync. Okay? Let's say you want to rsync a drive to another drive across the network, or maybe just locally even. And let's say the source is live. So as you're doing the rsync, the source is getting updated. By the time the rsync is finished, there's been changes that you don't have on the destination. So you do another rsync. This will be quicker because that delta is small, but again, you're going to have changes. Rsync can get you close, but can't get you exact on having a consistent source and destination. With snapshots, you can. The snapshots aren't changing, right? They're read-only. So when I ZFS send a snapshot to another data set or to another pool, when it finishes, they're both exactly the same. Okay? You could SHA-256 sum them, and you'll get the same SHA-256 sum. Okay? What's fun about this now is it operates over standard out when you send something. So you can redirect it to a file. You could pipe it through OpenSSL or GPG to encrypt it and then send it to a file. You could pipe it over SSH to send it to your backup server, which is in California, and then the backup server have it do the ZFS receive and put it into a normal data set. So ZFS send sends it to standard out. ZFS receive looks for something on standard in. Okay? Put any sort of mixture of tools in between that mix, and you're using the Unix way, right? One tool to rule, or one tool to do one and one thing well, and a whole suite of tools for this sort of thing. So this is a great way to back up your data, because snapshots aren't a backup. They're stored locally on the same pool as the rest of your disks. Those disks die. Your data center gets hit with a nuclear bomb. The data's gone, right? So you should ZFS send it to a backup storage server, so in the event of a failure, you can ZFS send it off the backup back into the live running system.
And with the snapshots, I'm trying to remember, with LVM, when you make a snapshot, doesn't it reduce the performance of your drive?
LVM snapshots are horrid. They're not implemented well, yeah.
And with ZFS, it sounds like from how you described it, it wouldn't.
It's not a performance penalty. It doesn't incur a performance penalty at all. When sending and receiving, it's also ionized. So any data that needs to use the disk, it'll step out of the way, but continue to work.
Right, or just with the LVM, it's basically keeping out of.
Right, so with LVM, the idea is the same. Yeah. With a snapshot, as data modifies, you start copying deltas into the snapshot to keep the data consistent. With LVM, though, you create a new logical volume, and you tell it the size you want it to do. Right? With LVM, all your logical volumes are static sizes. And now that it's a snapshot, as data is changing, those deltas are being brought into the snapshot. What's unfortunate is the performance is bad. For one or two snapshots, it's not a big deal. But when the snapshots start getting big or the deltas are frequent, it really...
Isn't it kind of writing everything twice? Or?
It's pwning the disk. It really thrashes the disk. Yeah, LVM snapshots, unfortunately, aren't implemented very well.
With ZFS, because it's natively Copyonwrite, it just leaves the old copy and keeps on.
Right. So the snapshot just gets a copy of the Merkel tree, which is basically just a small file, and stores that small file. And then it knows my data stored here for this block, and so forth. If that block changes, I want the original contents before the change gets applied. But it's not. In fact, if I had internet, I could show you on my production server. Only a couple minutes left.
The Utah open source Is it
Oh, that's okay. But
anyway?
yeah, I don't want to keep us too late. I have a RAID 10 setup, and I'm doing that snapshotting regularly and consistently, and I don't notice any performance. I've got Munin graphs that show my disk utilization and my throughput, and it's sailing nice and fine. So, ZVols, if you'll notice up to this point, ZFS has not presented me any block device. I've never had a block device that I format. I don't have a block device that I mount like you would with XT4. This is all the mounting, everything has been handled internally. ZVols are different. With ZFS Create -cap V, and I give it a size, I can create a ZVol. And this is an exportable block device that will register itself under /dev. What's nice about this is then I could export this block device over iSCSI, or I could make this the storage for a virtual machine on VMware or KVM. I could format this with XT4 and store data on it that way. It's a block device. Okay, so whatever I have of block devices, ZVols make that possible. ZFS has native support for sharing your data sets via NFS, Samba, and iSCSI. The reason for this is ZFS can make sure that the data set is mounted before the sharing begins. Say for NFS, if an NFS client sees that the export is available, it'll start writing data to it. But maybe the mount point on the server that's responsible for storing that data hasn't been mounted to the directory. The directory is exported, but the mount point's not mounted. And so now we have a problem with data consistency. ZFS can make sure that we have the mount available, then we'll go ahead and do the export. All of the NFS stuff that you're familiar with in Linux is supported in ZFS. Samba support is there. In my experience, it's been buggy. Lots of people disagree with me. I've had some fun discussions on mailing lists and chat IRC channels. And iSCSI support just isn't there. There's a listed bug. We're working on it. But all I would do is say ZFS set share NFS or share SMB or share iSCSI on my data set. Data sets also have properties. I can set compression as we saw, and I can also read some certain properties like my compress ratio. I can change my mount point. If you want your home directory to be on ZFS, but rather than mounting it to say /tank/home, you can mount it to /home/Aaron or Steve. Snapdir is what I talked about with that .zfs. By default, its property is hidden. If you set it to visible, then when you do an ls-a, the .zfs directory will show up. And sync has three options. You can do sync equals always, sync equals standard, or sync equals disabled. Sync, the default is sync equals standard, which means if an application wants to do asynchronous data, ZFS will step out of the way and let it do its asynchronous operation. But if it wants to do synchronous data, ZFS will force the synchronous write. You can force it with sync equals always, or you can disable it entirely with sync equals disabled. We can have a discussion about this later, but I actually advocate for setting sync equals disabled. Because the transactions are always in order, you'll never, ever, ever have a transaction out of order, even though you have asynchronous writes. Worst case, you have a catastrophe. You have old data because of the atomic nature of ZFS, and not a corrupted file system. You can still have a corrupted file even with sync equals always. So turning on sync equals disabled just increases your performance, and it doesn't increase your risk of a corrupted file system. Some best practices and caveats: enable compression by default, snapshot regularly and frequently. When sending snapshots, you can use incremental sends, like similar to an rsync. So you say you have snapshot 1 and snapshot 2. You send snapshot 1, that's the full send of all the data off to the remote server. But then just send the delta between snapshot 1 and snapshot 2. Don't do the full send to snapshot 2. This can help decrease, bandwidth, and let's be more efficient and more smart about things. There's a bug with GNU Linux. It's being worked on, but the ARC by default will chew through all of your RAM unless you set a cap on it. So for the kernel module, you can, in like etc modules, you can set the option ZFS ARC max equals, in this case 2 gigs, to cap your arc at a specific size. So it will require unloading the module and reloading it. Okay, I kept you a few minutes late. Are there any questions, comments, or rude remarks?
What's the link to this presentation?
It is, so here's a few resources. Presentation is toponce.org/presents/ZFS. That's where this is stored. I wrote a series of blog posts about system admin, like a system admin guide to ZFS. If you go to the zfsonlinux.org link and click on documentation, you'll find my guide listed there. Or you can go to p3.org/category/ZFS, and you'll find it all there too. And this is where you'll find my post about why you should use ECC RAM for your ZFS. And then, of course, there's my email if you have questions. Any other questions?
Is there any performance hits on deduplication?
When it spills to...
I mean, when it stays within one?
No. If the deduplication stable stays in RAM, the lookups are cheap, and you won't notice a performance hit. Now, if you have a cache device, I didn't mention this, but if you have a cache device and you fill up, your deduplication table fills up its allocated space in RAM, it will spill to the cache device. And if the cache device is a fast SSD, maybe a PCI Express SSD, then the IOPS can be as good or better than your DDR3, so you won't notice a performance hit there either. So if you can afford it, that can work. That's a good option. But once you spill the disk, your performance will decrease tenfold easily. So,
Okay. Thanks.
Yep, you bet. And that's actually my next post is the actual physical cost of deduplication. I'm hoping to have that up tonight about how much it costs for all of your platters, how much space savings you can get out of deduplication, so how much money you could save purchasing those platters, how much money it would cost for your RAM and your SSD, and then we'll weigh everything and see if it's worth it.
Where it optimizes?
Right. So we'll look at enterprise stuff with 15K SAS drives, and then we'll look at commodity 7200 RPM disks with cheap SSDs, and let's see where the cards fall. Tonight. Yeah. I was hoping to have it up before I came, but it didn't happen. So yeah, I'll work on it tonight. So.
Yeah, I was going to ask you about using cheap SSD disks.
So the MLC SSDs are fine. That's what I'm using, and they work just fine. With that said, there are some reliable MLC SSDs, like the Intel 320 and 330 series. You pay a little bit of a premium price for them, but they're rock solid versus maybe like the OCZ Vertex, which has had a rocky past. So yeah, I do some research, but commodity SSDs will work just fine.
Okay.
So,
especially if you have them mirrored in the...
For your slog, and yep.
I don't know, CZ that lasted me for 5 years.
Yeah. Did you hear that OCZ is filing bankruptcy?
No.
Yeah. They filed for bankruptcy until Toshiba is interested in purchasing the company. So, any other questions?
Yeah. First off, thanks for the blog series. That was very helpful.
Yep, you bet.
Let's say I've got a laptop with multiple hard drives in it that doesn't have RAID capability, and I want to use the RAID Z features to speed things up. Can I boot to a Debian-based system?
So
RAID Z?
yeah, so this is interesting. FreeBSD also has ZFS support, as you probably know, and they have full ZFS root support. So for your root file system, everything is ZFS. We're almost there with Linux. The problem is our grub, we just need to get patched to load a ZFS module in grub so we can get the kernel off of it and start the boot process. I have a friend who does have a ZFS root install on his Ubuntu workstation. With that said, he's noticed some interesting oddities. It's not bulletproof. It's not there yet, but people are pushing it. People are creating bugs. The ZFS on Linux project is working on it. They even have it as part of the roadmap when they want to have it finished. So it's there, it's functional, but you might discover some weird things about it. So for myself, on my workstation at work, I just have ZFS for my home directory. I don't have it for root. So.
Yeah, Yeah, I tried it with the VSD this weekend, and it installed all right, but then when I tried rebooting, I learned my laptop's not good for virtualization.
Gotcha. Cool.
With virtualization, is the only way to do, well, I assume you could share them over NFS.
So there's a few things you could do.
Sharing the whole, or doing the volume thing seems like it'd be a lot less efficient.
The zvols?
Yeah.
So yeah, you could definitely do the zvols. You're setting a static size. So if you know that your virtual machine needs 100 gigs, just create a 100 gig zvol, and then,
but you don't get, I mean, because then you wouldn't have, like you said, you have to set a certain size. You can't just share all the space.
Right. I'm not sure if I'm not sure if you can grow zvols actually. Not 100% about that. So there are some limitations there. The virtualization route I went is virtualization images. So I made the data set. So from QEMU, I'm using KVM. So from QEMU's point of view, I said, here's a directory that I want all the VM images to be stored in, and that directory is just a ZFS data set. And then I can just go through and say, create 100 gig. And through QEMU, I can grow or shrink the image file. I can have all that goodness. So I haven't benchmarked. This would be an interesting blog post, I guess, now that I think about it, is performance benchmarks on using virtual machine images versus using zvols. That would be, I think, something fun to do, but I haven't done that.
Shall we throw away our bacular scripts?
I don't know if I can answer that question. We've deployed ZFS at a number of different locations at XMission. One of those is our centralized local backup server. And we found that for 90% of the use cases, it works just fine. But then we have these one-off oddity systems that we still rely on, we're using backup PC for, that we still rely on backup PC to get the data to the server.
Windows or Windows stations?
No, we actually don't have any Windows servers in XMission at all. So, no, they're either old and crusty, or it's just, each of them has just some weird thing about it. So, I wouldn't recommend throwing away your bacular scripts. But you could probably find that with the ZFS sends and receives, that it probably...
But it sounds pretty safe to play around with this on a dev server.
Yeah. So. That is one thing that I've noticed, and I filed this as a bug, and it's scheduled to be fixed by 0.6.7, is if you snapshot as frequently as I do, after each snapshot, I was sending my data. I was actually just a little 500 gig external hard drive sitting on my workstation. After about 10 days, my workstation would kernel panic. After digging into it, I found that the ZFS send, when I'm sending that frequently, every 15 minutes, after about 10 days, So I stopped sending every 15 minutes. I send every day, and my workstation reboots often enough that that's not a problem. But in production, we actually stopped doing ZFS sends until this bug gets fixed, because we can't afford a kernel panic in production. There's no way. Even if it's once every 6 months, if I can avoid it, I'm going to avoid it.
You guys use this in any production?
Mirrors.xmission.com is on a ZFS pool. Our backup servers are all on ZFS. We have what we call a remote drive product that we sell to customers. Underneath it is ZFS. Our staff home stuff is on ZFS. Yep. We're slowly pushing out. It's not on all our servers. We have about 200 servers, and probably 190 of them are XT4. But we're getting there.
Setup again, when you do a new setup, do you go in with all new hardware?
I wish we had the budget to do that. It depends. It depends. Depends on the setup. Usually we reuse a lot of old hardware, or we have...
But you try to match them up like you were talking about.
Yeah, absolutely. Yep.
Do you use... on your VMs, do you use ZFS on top of ZFS, basically?
No, in my VMs, they're XT4 file systems. Because I know that they're sitting on top of a ZFS install, I'm not concerned about the data. So, Yep, I'm all right. So.
Could you use like ext2 or?
Sure. Yeah, in fact, that's another interesting discussion is because ZFS has all this checksumming and this atomic transaction rights and its Copyonwrite and the whole 9 yards, do I really need a journaled file system inside of a virtual machine that's residing on it?
Right.
I've had this discussion with some of the admins at XMission, and this is something we'd like to test is XT2 only does 2 writes, inodes and data blocks, and you're done. XT3 has to do 4. XT4 does more because it has to do an extent allocator, it has to update the B tree. So we could get significant performance gains if we remove all of that junk. But then what are we risking? So, I mean, there's probably some deep file system internal levels that I don't even understand that I'm overlooking.
Yeah.
But I think that would absolutely be something worth looking into, for sure.
It'd be interesting if there was some way, you know, like the VirtIO device
Mhm.
lets you kind of.
Yeah, you can do right through or right back, right?
Yeah.
Mhm.
But if there's some way to basically have access to the pools in the
Natively.
host, so if you could access that pool, you know, or have something exported to that.
Right. And I think
kinda-
maybe the zvols and just presenting the zvol, but yeah,
Right.
yeah,
Yeah.
be interesting. Cool.
Okay.
Any other questions? All right. Thanks, guys.